A warm welcome to all our participants, Russian and Swedish, living around the Baltic Sea, a very important sea that we share together. My name is Eva Sundqvist, and I'm the Consul General here in St. Petersburg. We are trying to build bridges between Sweden and Russia, and our mutual environment is, of course, the most important thing we are discussing right now. And therefore, we are especially proud and happy to start this Swedish-Russian project today with the help of the University in Stockholm and and more specifically the Baltic Sea Centre and Gun Rudqvist, who will be our moderator today. And we are just equally happy and proud to present Olga Rublevskaya from Vodokanal. I think if you are from Sweden and you don't know exactly what Vodokanal is, it's like Henriksdal's reningsverk, but much, much bigger. And we are also happy to welcome Emma Undeman from the Stockholm University. So warm welcome everyone, and Gun, please, the screen is yours.
Thank you very much, Eva. Good morning, everybody, and warm welcome. I would also like to say that to this first kickoff seminar, trying to bridge even better the collaboration between Sweden, Russia, and the other countries around the Baltic Sea. We, the Stockholm University Baltic Sea Centre, we are very happy to start this collaboration with the Consulate in St. Petersburg, and especially with our Russian colleagues, can be, for instance, as today, with the interesting company Vodokanal, and also, of course, with other researchers around the Baltic Sea. Just a few words about the Baltic Sea Centre before we head into today's topic, which will be wastewater treatment and why it's relevant to try to treat wastewater even more than today, to reduce the amount of chemical pollutants in the Baltic Sea. The Baltic Sea Centre, we are, of course, a part of Stockholm University, and we do research. I mean, of course, we are the university. And a lot of the research that's being done concerns all the different environmental aspects of the Baltic Sea. And we collaborate and support stakeholders with this research. And for instance, HELCOM, you know, this joint body for all of us around the Baltic Sea, aiming at improving the health of the sea, they lean to a great extent on research performed and led by the Baltic Sea Centre. For instance, the modeling of amounts of effluents reaching the sea. But we don't only do research, we also have a wonderful field station just south of Stockholm. It's a great place for collaboration with international researchers. And we also have a mission to try to work in different manners to bridge the gap between policy and research. So we do this in different manners. And one thing can be this kind of webinars, a Baltic breakfast. And please go to our webpage to see other themes of breakfast, because we do them continuously, not only this version with the consulate, but we do them once a month on different topics. Most of them are, you know, a mixed Swedish-English, but some of them are only in Swedish, but that's easy to find out. So I'm Gun Rudqvist, and I'm head of policy there at the Baltic Sea Centre, and I will be moderating today's topic. So let's dive right into what we're going to talk about today. So the title is Better Treatment of Municipal Wastewater a Good Way to Reduce the Flow of Micropollutants to the Baltic Sea? We know that chemical pollution of the sea is an increasing problem. And we can know that micropollutants can get to the sea in all kinds of manners. And we will start by having our researcher Emma Undeman. She's an Associate Professor of Environmental Science at Stockholm University Baltic Sea Centre. And she will give us an overview of the research, what you know today about micropollutants, and a recent project that's been done in collaboration with other researchers around the sea. And thereafter, we will have Madam Olga Rublevskaya, who's the Director of Technology Development Department at this wastewater treatment plant, Vodokanal, in St. Petersburg. And she will give us a presentation on the existing technology of wastewater treatment in St. Petersburg and the potential of a more advanced wastewater treatment. And thereafter, we will have some time for questions. So if you are following this seminar here via Zoom, you can ask questions in the chat in English or in Russian, and we'll make sure it'll be translated and get to me, and I will try to post them after the presentations. But also, if you listen via the YouTube channel, you can go to the comment field and put questions there. And we will try to make sure that we finish around 9:45 Swedish time, 10:45 St. Petersburg time. So great to have you all there, and I will give the floor to Emma Undeman. Please, Emma.
Okay. So yeah, thank you very much for having me here today. I will tell you a little bit about advanced wastewater treatment, what that is, and discuss a bit if this can be a good way to reduce loads and levels of chemical contaminants in the Baltic Sea. And as you may know, our surface waters are impacted by thousands of chemicals that are released into the aquatic environment, and primarily or exclusively as a result of human activities. And there are, as Gun mentioned, several pathways that these chemicals can take to reach the Baltic Sea, depending on how they are emitted and also the chemicals' inherent properties, like volatility or water solubility or hydrophobicity. And they may travel via air and enter the sea via atmospheric deposition, or they can deposit on land, and then this is followed by transport via runoff and transport in rivers. And other chemicals are, of course, emitted directly to land or water. And we don't actually know which chemicals that make it to the sea or which pathways they come by in most cases. But we do know that wastewater treatment plants are important collection points for many diffusely emitted chemicals in our society. And how this pathway compares with other transport routes, that can be more or less easy to determine. For example, most pharmaceuticals is obviously the major transport pathways in many cases. But for other chemicals like flame retardants or plastic additives, it's more difficult to generalize, and they can actually take several different pathways to reach the sea, and it's hard to know which one is the major one. But when we look in wastewater wastewater treatment plants, we do find a wide range of chemicals when we look for them. And conventional wastewater treatment plants, they can have different setups with different treatment technologies, but they are all designed primarily to remove oxygen-consuming organic material and nutrients. But despite this, many of these chemical contaminants, so-called micropollutants, they are removed anyway via different processes. It depends on their molecular structure and the conditions in the wastewater treatment plant. They can be lost via volatilization, or they can be degraded during the treatment process, or they can sorb to particles which then sediment out of the wastewater stream and becomes the sludge. But a certain fraction of the chemical load passes through the treatment and is emitted via the effluents. And just to show you some examples, this graph here, it shows a typical removal efficiency of a range of chemicals, mainly pharmaceuticals here, and the removal efficiency is here on the y-axis. A typical removal efficiency in a conventional treatment plant. This is data compiled from the scientific literature. And you can see that it is it's very variable how much of the chemical that is removed during conventional treatment. I show a few examples. For example, pharmaceutical carbamazepine is not so well removed. Diclofenac is a common drug also that is not so well removed, whereas ibuprofen and paracetamol are quite well removed, although there is no special treatment for these pharmaceuticals. So it's very variable, and you can say that in general maybe half the load of the micropollutants are already removed in a conventional treatment. But there are possibilities to improve this removal efficiency. And this is what is discussed a lot. If you use technologies that specifically target micropollutants, and these you can have it all either integrated in the treatment or as an additional step afterwards, the conventional treatment. And these technologies, they are based on different fundamental mechanisms. It can be filtration, a better filtration of the wastewater. It can be technology based on oxidation, for example, using ozone, or it can be adsorption to activated carbon, or it can be biological, enhanced biological degradation. So, and there are also other techniques, but these are the ones that are used, for example, in full-scale applications. But the efficiency of these technologies is dependent on how they are used. For example, the dose of ozone that is used or the amount of activated carbon. So if we look again into the literature where these advanced technologies have been used in full-scale applications, the additional removal is often around 70 to 80% for the individual chemicals. And this is partly because, as I said, it depends on the dose you use of ozone or activated carbon. So this kind of removal is what you often aim for when setting up the treatment. And the improvement of this total removal during the treatment is, of course, dependent on how well the chemical was removed in the first place. You can see there's a quite large increase in the total removal for carbamazepine, and diclofenac can be removed to a large extent, whereas for ibuprofen and paracetamol, the additional gain of this treatment is, of course, lower because these substances were already well removed in the conventional treatment. Yeah, and it can also be, I can also comment here that this is examples for activated carbon. And this graph would look different if it was ozonation, because, as I said, these technologies are based on different fundamental mechanisms and the efficiency is different for different substances. Some substances are very stable and are not so susceptible to ozonation, for example. So it's often discussed that we need to have combinations of different types of advanced treatments that have different mechanisms to get a broader range in this removal. Okay, so today there's a debate regarding the use of advanced treatment of municipal wastewater, if this is something we should invest in. And there are certainly both pros and cons with advanced treatment. So on the positive side, this is a broad measure. It doesn't target a specific compound, but the treatment will generally decrease the concentrations of micropollutants that are emitted. For some of them, it will be almost complete removal, and for others, this will not have a big influence. It's good that it can remove both known and unknown substances that we are not aware of in the wastewater, including also transformation products of substances. So it can be viewed as a precautionary measure, maybe a safety net that can capture substances that have slipped through our regulatory net. And these technologies, they already exist and are implemented in quite many wastewater treatment plants, for example, in countries like Germany and Switzerland and other parts of the world. And it is believed that if this implementation gets wider, it will also help technology development and make these technologies better and less energy demanding. Because this is, of course, the big drawback, that this costs money and energy. And who should pay for this? Should the households pay with higher prices for the water, or can we make the producers of the chemicals pay for cleaning the water from their products, following the polluter pays polluters pay principle. Another argument that is used against this is that not all micropollutants can be removed anyway. We cannot rely exclusively on this measure. And if we use ozone, we will actually form other transformation products, as ozone, as it's not always full mineralization in this process. And this is not viewed as a sustainable measure, as it's a fundamental principle that pollution should be stopped at the source, and the wastewater treatment plants are not sources of these pollutants. They are merely transport pathways. In this debate, it's also stated that it's not clear that this is really needed. It's not proven that, for example, wildlife populations are negatively impacted by wastewater. We cannot see effects at population level. And so this means that it's unknown what the true benefit would be of this measure. This is a problem when you have measures that are implemented of precaution, that you don't know what you really gain in the end. Yeah, but so let's have a look at the Baltic Sea then. What is the problem here? Well, we can see that there are certainly studies that show that observed levels of micropollutants in European river water are likely to cause both acute and chronic effects on aquatic organisms. But in the Baltic Sea, we have a high dilution. So levels of most substances are lower, but we can see that there are elevated levels in many coastal waters. And this is partly due to the continuous emissions from wastewater treatment plants and river water. And we can see that there are gradients with highest levels close to urban areas, for example, in the Stockholm archipelago. But some micropollutants are also detected in the open sea water, which indicates that they are persistent enough to build up in the entire Baltic Sea. And it is mainly pharmaceuticals that have been measured in the water phase, but also other polar organic micropollutants like corrosion inhibitors and pesticides and flame retardants and a wide range of chemicals. You can see I show here some data from 2 different studies, and you can see that the levels in the median levels are often maybe below 100 nanograms per liter, but you can see occasionally much higher concentrations, in particular in the coastal zones. So we know that we find these pharmaceuticals in particular in the coastal zones. And this graph here shows a compilation of data from wastewater treatment plants in the Baltic Sea region that we have been working with lately. And you can see if you look at different types of chemicals, here are pharmaceuticals, and here are metals and industrial chemicals and ingredients in household and personal care products and pesticides and some classical pollutants like PHs, PCBs and dioxins. You can see that many pharmaceuticals are present in very high levels in wastewater. This is a logarithmic scale in nanograms per liter on the y-axis. But we can see that many industrial chemicals and other types of chemicals are present in as high levels in the wastewater. So we can suspect that a wide range of other substances than pharmaceuticals are present in our coastal waters. But are these levels too high? I mean, the mere presence of chemicals in wastewater and in the Baltic Sea is perhaps not an argument to invest in expensive treatment technologies, because we are, after all, able to detect lower and lower levels of more and more chemicals because of the development of analytical methods. And unfortunately, it is extremely difficult to judge if the chemical mixture emitted from wastewater treatment plants is a large threat compared to other chemical inputs. We can see that levels of many individual substances, when we look for them, they are often exceeding this predicted no effect concentration, for example, at river mouths and in coastal waters. But looking at the combined toxicity is perhaps more relevant, and this is what is now a big research area. You can look at this example, for example, a study from Sweden, when researchers were looking at 172 known river and wastewater treatment contaminants. They were looking for these also in coastal water and found 62 of them in the coastal waters. And they then calculated their combined toxicity. I show here data from 3 locations that they produced. And on the x-axis, you have different substances, and on the y-axis, you can see their contribution to the total toxicity. And if this exceeds 1, you are likely to see an effect of the combined effect of these substances. And the researchers could see that in all these locations, if you add up the toxicity of the different chemicals that they could detect, this would give an effect, but not always for the individual. If they have measured, for example, only naproxen here, they would not see a toxic level. But if you combine that with other substances, you will exceed the toxicity threshold here. But they could also see that actually of these 62 substances, it was actually just a few of them that were responsible for the major part of this combined toxicity. But on the other hand, it was not always the same substances in the different locations. So this is really a difficult task to judge if this combined toxicity, how this is impacting the sea. And it's unknown what, when you do these kind of assessments, it's hard to say what kind of consequences you will have at population level in the different species. And it's hard to compare this to other stressors in this area. But when considering better treatment of wastewater, it is also important to clarify what the goal is, because it's often argued that it is not reasonable to put requirements on all wastewater treatment plants to implement this kind of treatment, because it's in particular expensive to do this at smaller wastewater treatment plants, and it requires competence and capacity to operate these advanced treatments. So which plants should be upgraded? And this depends on what the goal is. If the goal is to reduce the total load of chemicals, which is relevant mainly perhaps for persistent substances that can travel in the catchment and will build up in the Baltic Sea, then it is the best idea is to go for the larger wastewater treatment plants, because they are responsible for the largest load of chemicals in general. But if you want to reduce locally elevated concentrations downstream wastewater treatment plants, here you can have high levels because of continuous emissions of substances that may not be particularly persistent. It's called pseudo-persistent substances, or pseudo-persistence, that you have high levels, although the chemicals are in fact degraded quite quickly. And here you have to consider the size of the wastewater treatment plant, but also the dilution in the water that receives the wastewater. So I will show here an example from the CV Pharma project that was recently finalized, a Finnish project where they have calculated the loads of pharmaceuticals in different coastal areas. And they also calculated concentrations in river water entering the Baltic Sea. And you can see that the loads of pharmaceuticals, which was what they were studying, it's correlated with population density. And concentrations, they correlate more with dilution in the river water. So if you look here, for example, at the German coast, the green colors here indicate that you have a little bit lower loads here. It's probably not a large population, but because of a low dilution, small volumes of river water, you actually have quite high concentrations in this coastal area, or in this river water entering the coastal area. On the other hand, if we look here at the Gulf of Finland, they're predicted to be rather high loads, for example, because of the large population in St. Petersburg. But in many of these rivers, you have also a high water flow, so you don't have so high concentrations. So what you want to do, so you have to separate if you want to reduce the loads or reduce the concentrations in the coastal water. These are two different goals. So to sum up, the question here of if we should use advanced treatment, it's not so easy to answer, but considering the knowledge we have today, I think the strongest argument, as I see it, is that this is a precautionary measure that can be used both to reduce the amount of relatively persistent and mobile substances that can travel in the catchment, but also to protect coastal zones with elevated concentrations due to these continuous emissions. But you have to consider what you want to achieve when you decide which wastewater treatment plants to implement this in. And I think we should take advantage of developments in analytical chemistry, like non-target analysis and ecotoxicology, and try to better understand how the coastal areas are in fact impacted by micropollutants and how large fraction of the chemical load that has passed through wastewater treatment plants and what fraction of the negative effects that actually originate from wastewater treatment plants. These are really tricky questions. That was all I had to say. Thank you very much.
Thank you very much, Emma. Just a short follow-up question before we will continue with Madam Rublevskaya, and then we will get back to a more general common discussion. We first have a more detailed hands-on question coming in from the chat. A question is activated carbon renewable, or is it a steady new supply needed in the wastewater treatment?
Yeah, that is a problem, that you have to regenerate the carbon or exchange it because it gets saturated after a while. So this is part of why it's energy demanding, and it's impractical in that sense.
Okay. It was interesting to listen to your pros and cons and the problems that you told us about based on the fact that we know today too little about the different chemicals entering society. And I know that you sometimes really stress the fact that the amount of chemicals entering society is enormous, of course, and the information that we have around these chemicals are still very, very low. So if I understand you correctly, given that background, you still would say that since we have the advanced wastewater treatment, is it still a good thing to use from the precautionary principle perspective?
Yeah, I mean, that is what it would be out of precaution, because it is true that we have to, of course, stop the emissions of hazardous substances at the source. But we, at the same time, it is clear that although we have an ambitious chemicals legislation, it is very hard to find out which chemicals that we need to phase out. The identification of hazardous substances is a challenge, and it takes time also to do this. So although we have some rules in place, it takes time to actually go through the long list of chemicals that are on the market. So I think that, and there's also many gaps in this legislation. For example, we do not consider transformation products of the substances. So this can be viewed maybe as an opportunity to do, because here we have many of the substances collected. But again, it's not always that this will help, because some substances do not take this route to the sea. So it is very variable, but today it's hard to say which ones do, which ones don't.
Okay. But as you stressed, we can do this, but we cannot stop working at the source. Right?
No, that will always be needed, and that is the ultimate goal, that we have, that we only use chemicals that are sustainable, and then we don't need this kind of treatment or end of pipe solutions either.
But that's a still far-reaching goal. I mean, it's way ahead.
I think it will take quite some time before we are there.
Okay. Thank you, Emma. And now we will continue with Mrs. Rublevskaya, who's the Director of the Technology Development Department at Vodokanal. Please, Olga.
Good morning, everyone. In my presentation, I will tell which events does Vodokanal do to reduce the pollutants that pass onto the water bodies of the city. St. Petersburg is the largest metropolis of Russia in the north that sits in the water basin in the catchment area of the Baltic Sea. Today, more than 2.1 million cubic meters of wastewater is discharged into the sea. We have 21 wastewater treatment plants functioning in the city. 13 of them are aimed at treating household and combined wastewater. 8 wastewater treatment plants are there to process surface runoffs. The sewage system of our city is built in such a way that the major area, we've got more than 70%, works as a combined wastewater disposal system, meaning that all the runoffs that the city produces go into one single disposal system. It's the rainwater, it's the industrial wastewater, it's the household wastewater, and all of the 30% of the territory, meaning the new districts and the embankment areas of the city, has a separate system where the surface runoff is collected separately from household and industrial wastewaters. St. Petersburg sits in the Baltic, on the Baltic Sea. That's why, treating our waters, we have to abide by the HELCOM recommendations that Russia has subscribed to in 1998. And since then, everything we do have to abide by the HELCOM, the Helsinki Convention. One of the major things we do throughout all those years is we deliver on our program to stop untreated wastewater discharge in St. Petersburg. Until 1978, all of the wastewater in the city directly was discharged into the water bodies, including the Neva River, which is the main source of drinking water for the city. This slide contains some of the key milestones that helped us, by 2021, to record the level of treatment equaling 99.5%. The quality of treatment itself at our facilities is regulated by the existing applicable Russian legislation as well as by international HELCOM recommendations. Talking about the Russian legislation, starting from 2019, a new law has been passed, which actually separates the responsibility and the obligations for the pollutants discharged between Vodokanal and our subscribers or our customers. Vodokanal is currently responsible for some of the pollutants that are characteristic of the industrial discharges, meaning BOD5, CODs, compounds of nitrogen, phosphorus groups, and microorganisms. And the technological solutions that we try to implement at our wastewater facilities are mainly aimed at increasing the efficiency of treating these pollutants. Our subscribers or customers are currently responsible for their specific pollutants, which are characteristic for their plants and their production sites. This slide lists some of the indicators, some of the threshold levels which we set for our largest wastewater treatment facilities. So, when discharging the water into the Baltic Sea, they need to comply with these standards. According to our legislation, we're now using a fit approach, a floating approach, depending on the size of the facility, depending on the water body where we discharge it to. We will define specific characteristics based on these aspects. And the requirements we currently have for some of the largest wastewater treatment facility. The biggest one process 1.5 billion cubic meters a day. The lowest process 10,000 cubic meters a day. So the requirements are less harsh because previously all the wastewater treatment plants had to deliver on the level that was used by fishery quality of water. But having this fit approach helps us to propose more efficient measures of treatment. Still, I need to mention that every time we perfect our treatment processes, we want to aim at such indicators, at such levels of pollutants that are characteristic for fisheries. But of course, we are relieving some of the wastewater treatments with the unnecessary treatment operations. Let's have a look at the share of fees. 80% of the fees that we collect are for specific pollutants. The fees that we are paying for other kind of chemicals and substances are much lower, because that's exactly what we're doing, to reduce those chemicals in the discharges. Let me talk you and quickly go through the treatment system we've got. I think we can divide it into several blocks. The first block, a big one, is the mechanical treatment, which has shale shaker screens, grid chambers, sedimentation tanks. Next, we have biological treatment, aeration tanks, and sedimentation tanks. And in pink, I'm also showing two other blocks that currently have been introduced. We don't have them on all of our wastewater treatments yet. This is something that we call tertiary treatment and disinfection. Let me explain you how the biological treatment works. That's the main element of our process today. And we pay a lot of attention keeping it up to date, because it's thanks to biology that we can achieve the necessary quality of our waters. Biogenic elements, biogenic characteristics are the main things that are dictated by the HELCOM. I said that we have a combined discharge at about 70% of the city. And of course, all of our runoffs are very rich in organics, because of course they're diluted by surface runoffs, by rainwater. That's why what we're introducing right now is washing and pressing of waste from screens. It helps us to recuperate some of the organic materials and substances. We also use pre-fermentation of raw sludge. Let me explain which biological treatment systems are working at our plants. The first one we introduced, it's a Russian technology called Krial. This technology provided that the air tank will be divided into different zones with different oxygen regimes. But during the operations, during the performance of this tank, we found out a couple of disadvantages. The thing is that we were doing bubbling with coarse bubble aeration. And of course, at lower temperatures, what we can see is the dilution, this dissolution of this air. That's why those zones are not that efficient. Today, what we're trying to do step by step is to use the Cape Town and Hesburgh's University technologies, because they provide for mixes in anaerobic zones, which, well, does not let air go in. And we can also manage the system in a more flexible way, and we can do a much deeper processing and a much more deeper treatment. But even though all of those things are being done at our wastewater treatment plants, we sometimes need to apply additional measures, and those additional measures require chemical methods of removing phosphorus or phosphates. The introduction of new reagents or new chemical agents helps us to catch phosphates from the system by dosing the special removal agent, and in doing so, we're reducing the load to our treatment facilities, main treatment facilities, so the phosphorus load is reduced. And in this way, we're stably cleaning our discharge from biogenes. In the future, we're also planning to implement some of the tertiary treatments. Today, we're testing a couple of technologies that are currently available in the market. You can have a look at them here on the screen, and we understand that tertiary treatment processes helps us to, well, reduce a lot of pollutants, especially in solid phase in the cleaned water. And like you can see on the graph below, the lower solids, suspended solids you have in the wastewater, the more efficient is the disinfection process. The disinfection process has been introduced at about 20% of all of our treated waters. Usually we use ultraviolet radiation for disinfection, but we're searching for alternative means. of disinfection. We've tested a whole range of different chemical treatments to make sure that it works, like PAX 12, for example. Considering all the OPEX and CAPEX that needs to be invested, considering various secondary transformations or events, we think that still what's preferable is the UV disinfection. What's next for the plant, for Vodokanal, after all of the discharges? All of the household and municipal wastes and industrial wastes will be treated. Let me remind you that we still have 0.5% to deal with. We will definitely put all of our efforts on cleaning the surface runoffs, because 30% is only collected separately. We did some work with the Russian Academy of Science, and we found out that 30% of all the suspended solids that get into our sewage systems, they actually are collected from the surface runoffs. They get from the surface. That's why today we need to test and analyze and to find the most optimal solution that will help us to clean the surface runoff, the rainwater, and etc. The major thing that we need to use here, or the major system, is of course mechanical. Various accumulating reservoirs, mechanical treatments, sand removals, oil product removal processes, shale shakers, sieves, grates, and so on and so forth. We're testing a lot of solutions at the moment to find out the best. Of course, to achieve the necessary effect, we need to remove the sludge from the surface runoff. All of the sludge that we get at our wastewater treatment is dehydrated, and we bring it to 3 incineration plants, which we have in our city. The sludge incineration plants helped us to reduce the amount of sludge by 10 times, and we get the ash, the cinder, that doesn't have any pathogenic microflora, doesn't smell, and by doing so, we don't have to dump it, we don't have to waste it around the city. So we only have 2 dumps for the sludge here in the city. Everything else is being burned. Here's a gas treatment system plant that we have at our facilities. This gas treatment facility is fully compliant with the EU regulations and Russian norms and regulations that, mind you, are sometimes even more strict than the European ones. Now, when it comes to sludge processing, we want to use it as much as possible to recuperate and recycle it. We remove a lot of phosphorus from it, so the sludge is enriched with a whole number of minerals that can be quite useful for soil, for fertilization of that soil. And that's what we want to do. We want our wastewater treatment plant to be a completely waste-free, basically aiming at a circular economy in wastewater treatment plants. One of the activities that help us to reduce the load onto our wastewater treatment facilities is the introduction of snow melting machines. Previously, when the snow melted, a lot of stuff was getting into our wastewater treatment plants. Now, the snow melting facilities are being used, and that's why we don't get a lot of sand and waste on our WWTPs. But of course, the new time dictates the new solutions and of course puts up new challenges. Microplastics is a scourge of today. Together with the HELCOM committee and Helsinki Environmental Service, we did a pilot, we measured microplastics inputs and outputs. And we found out that all microplastics can be removed, of course, using current methods by almost 96%, just the current methods. But of course, this is not enough. Definitely, that's why an additional treatment measures will be required, and we hope to improve the removal effect. Now, talking about hazardous substances, we also carried out some of the tests about diclofenac and ethyl estradiol, and we see that at our wastewater treatment plants, we get a concentration of max 10 to 15%. Yes, those pharmaceuticals do take a transit route through our WWTPs, and that's why we need some new solutions to be able to control these indicators at WWTPs, to regulate them, and we definitely need new stages of treatment for these types of pollutants. That's it from me, and this is everything I get to say about what we do to reduce the load on our water facilities. Thank you so much.
Thank you so much, Olga. Very interesting and very impressive journey you've done through these last years in getting the wastewater cleaner and cleaner. And as I understand it, the tertiary step is the step sort of getting you closer to maybe what Emma was talking about, and you mentioned at the end, the advanced wastewater treatment, addressing hazardous substances. What are your bottlenecks? What would you need to see to get to take this next step?
When it comes to the tertiary step, I don't think there is a big barrier, or I don't think there is a bottleneck. We are doing it regularly on a step-by-step basis according to the budgets we've got and the amount of financing that is being allocated. Now we have 6 facilities that belong to the first category of negative load. These are the largest WWTPs, and according to our investment program and according to our schematic, according to our plan until 2025, we regularly carry out the events that needs to be done, the activities that needs to be done. It's just that today we are testing different solutions. We're choosing the most optimal one. For now, it seems like the most optimal are disc filters. Now, when it comes to pharmaceutical pollutants, today we're not being yet controlled by those indicators or by those pollutants. So for now, we don't see a specific need to introduce additional technical solutions because we don't really know anything about those technical solutions. And as far as I know, the new means of processing are still being researched. So in order to treat the pharmaceutical pollutants, we still need to assess the harm that they make and the damage that they do to the water basins and to the water bodies. And that will be the grounds to include pharmaceuticals into the list of KPIs that we're tracked against, and it will be the basis of introduction of a new technology. Because, of course, it will be reflected on the tariff, right? We will have to increase the price for the tariff, and it all has to be given legal grounds, so to speak.
Thank you. So if I understand you correctly, that will be a step depending on monitoring and more research on the effects on the water. An additional question, with all these improvements that you've done, can you see the effects, the general effects, not talking about hazardous substances, but general effects in the Gulf of Finland, you know, where you are located, like improved sight depth and things like that, that could see the improvement of reducing, for instance, phosphorus?
Yes, exactly. As far as the biogenic elements removal is concerned, we do see the effect. And we can mark it, we can measure it. We have HELCOM office here in St. Pete, and together with them on an annual basis, we do the assessments, we do the analysis. So we try to estimate the impact we make from the activities we introduce. And we see that now the biogenic elements are less and less getting into the effluents. Thanks to the technological solutions we're trying to implement across all of our WTPs, they produce this effect, and the effect is quite significant, I need to say. That's why, according to our data, I think we have the reason to believe that our efforts are not futile.
Thank you very much. Emma, just a final question actually to both of you. Well, we're wrapping up, time has run out. I'm sorry we're drawing a bit over time now, but this was so interesting, so I just took the liberty. So Emma, if you would like, this is your wish day. You can make a wish for what would you like to see to sort of speed up the work with advanced wastewater treatment, or actually more speed up the work with hindering chemical pollutants? And the same to you, Olga. What would you like to see? This is your wish day. And it will happen tomorrow, I promise. No. Please, Emma, go first.
Yeah, that's a difficult question, because when it comes to chemicals, we need to work in so many different with so many different aspects. I mean, this with advanced wastewater treatment, that is one possibility we have, but no one thinks this will solve everything. So we have to work with all these different parts at the same time. I think that's the only way you can get somewhere, by having parallel tracks that you follow. And I do think that it would be good if we investigated more. I mean, if you look at single chemicals in the wastewater, maybe you have too high levels of diclofenac. I don't think you will see that there's economy in treating the water just to remove one substance. I think you can never rely on thresholds for individual substances. We need to have a system where we look at the combined impact of everything that is in the water. And that is the tricky thing, because there are both known and unknown substances. So I think we need to develop a better system to look at combined effects and the total load, and judge if that is something we have to take any measures to reduce.
Thank you, Emma. And Olga, please.
What I dream about, my wish, is for all of our subscribers, meaning all of our clients and customers, to put down a local treatment facility at their own factories, because it will simplify our life, make it much better, it will help us to treat better, to treat more efficiently, and it will also help us to use the sludge in more ways. So it's going to be the first step, placing local treatment facilities at pollutants, at polluting companies. This is what will help us to get a minimal damage to our water bodies. Now, when it comes to specific pollutants and something that, well, where we can't really impact, where the local treatment can't impact, something that can come with urine, the urine can sometimes be a very strong pollutant with people use specific drugs or specific chemicals. Here we need to do an additional research. So my wish is that we do an additional research whether the technological solutions are actually feasible, whether they're actually needed to prevent any negative impact on the environment. These are my wishes. Thank you.
Thank you very much. We're going to wrap up now, but I see right now another more hands-on question, which I think is addressed to you, Olga, has come up. So if it's okay, I'll just put this as well. It says, sand from sand filter in the WWTP was transported to landfills. Are the MPs not released back into the environment? Does this make sense?
The sand that we currently catch at sand filters, we use aerated sand filters that help us to wash out the organics from the sand. So we separate organics from the sand. And later on, this sand can be used for, I don't know, for the foundations at our wastewater treatment facilities, for the construction purposes. The sand we don't really need to landfill the territories. We do take to the landfills where we take our ashes, yes, which is incinerated after the sludge is being, after the sludge collection. So you're asking about the sand filters, right? My colleague here is helping me. We don't have, well, additional sand filters. For the wastewater, sand filters are not being treated as a tertiary method.
Okay, thank you very much. So this was it for today. A warm thank you to Mrs. Rublevskaya and Mrs. Undeman, who has given us this important background and interesting information to take this discussion on how to stop chemical pollutants reaching the sea even further. And thank you to the Consulate, and goodbye from Baltic Sea Centre. And maybe I give the floor to you, Eva.
Oh, I just want to say thank you to everyone who made this first. Thank you to everyone who participated actively, and thank you also to Andrei, our fantastic interpreter. And I hope to see you all live sometime, but before then, we would like to just inform you that we are planning a new breakfast with Gun, of course, on the 21st of May. Correct me if I'm wrong, Gun, 21st of May. So I hope to see you all then. Thank you so much.
21st of May, and we will talk about climate change and effects on biodiversity in the sea and other aspects. So warm welcome back then, and have a nice weekend. Bye bye, everybody.